Hi everyone, my name is Anya. So welcome to the second part of the Faxage workshop of this afternoon. I'm going to be talking today about the aluminium alloy recycling simulations. I will be presenting part one, and my colleague Francis will be presenting the second part. So just to put everything in context, we know that alloys are not infinitely recyclable. And why is that? Is because when you mix and match alloys with different concentration and specification, and there's no purification, there will be an accumulation of alloying elements. This causes the recycled material to not fit the requirement and the specification for the original alloy that you intend to recycle, and you end up doing downcycling instead of recycling. Your alloy, generally alloy go to the cast sink, where it just simply mean like they're mainly recycled as cast alloys, even if they're originally wrought alloys. And because the tolerance for concentration of alloying element is higher. This is a problem because the supply for the alloy through recycling route may not match the demand on the market. So it is important to design safe and efficient recycling processes in order to ensure closed loop recycling as much as possible. And I will show you how we can use Faxage and thermodynamic calculation to achieve the design of such processes. So the example that we're going to be dealing with today is the universal beverage can recycling, which is a product that is one of the products that is the most recycled in North America. So before we get into the processes of the recycling of the UBC scrap, let us consider the composition of a can through the Alcoa standard. So the can is made mostly of 3000 series alloy, on which you can see in orange the composition. And this is, of course, the main material in the can. Some materials in the lid and the handle is made of 5000 series alloy. And you can see here the difference between the two is that the 5000 series is very poor in copper and is way richer in magnesium than the 3000 series. What we can see is in the red square is the scrap composition, or what we will assume to be the scrap composition, and it is simply the composition of a complete can, considering the proportion of both materials. So if we want to do recycling, we can either, if we want to get the material that it's useful, we can either try and retrieve the 5000 series alloy and a 3000 series. And if you make a quick comparison, one knows, or one can see that it would be easier to retrieve a 3000 series because we only have to remove the magnesium from the scrap. Whereas in the case of the 5000 series, we would have to remove copper, and this is not easily done because it is a more noble element than aluminum, meaning that it oxidizes, that it is harder to oxidize than aluminum, which is also the case for iron and silicon. So here the goal will be to remove the magnesium to fit those specifications. And like as I said earlier, copper and iron are tramp elements which are harder to remove. So typical secondary processes for demagging are depicted here. You can see different routes that can be taken. The fourth route is mainly getting another alloy through the use of hardener elements. The other routes are involving mainly reverberatory furnaces that are used to melt the scrap, and in which you can inject a gas that can be either chlorine or fluorine. This can be used to oxidize the magnesium in the scrap, so we can effectively remove it and form a molten salt. Another route is, instead of using a gas, we can use a salt flux in a crucible furnace to remove the impurities in the scrap. So let's get into the FactSage simulations. So the ones that we're going to see today is we're going to see 5 simulations. So the first one is about determining the operating condition of the furnace and the phase assemblage of the scrap. Simulation number 2 will be used to determine the heat balance of the furnace. Simulations 3 and 4 will be about the actual simulation of the magging processes. So either chlorination, which is the route 1, and using the salt flux, which is the route 3 that you've seen earlier. And finally, simulation 5 will be about showing the effect of air on the quality of the final product. So before we start, it is important to select the appropriate databases. So I will go this quickly. You've seen earlier that you can select different databases going in the select databases menu, in the data search menu. So the database that we need to select are FactPS, which is the pure substance databases and contains all the gaseous species. FT-Lite, which is used for aluminum alloy and magnesium alloy database, and it is used to describe the scrap, and both databases will be used for all simulation. Then we have the FT-Salt database, that is the inorganic salt databases, and in this case will be used to describe the formation of chloride salts in the demagging processes. So you will see it in simulations 3 and 4. Finally, the FT oxide database is used to describe all the oxidation product of the aluminum scrap, and it will be used in simulation 5. So now let's go into simulation 1. So if you want to follow the example, you can open the equi-ubc scrap composition.dat. So now you will see this window will open, and you see here the composition of the scrap, so all the elements that are present with aluminium. So here we're working in grams and on a basis of 1 kilogram of scrap. So one quick tip here, if you enter all the amount of the different alloying element and you want to quickly get the balance for the main element, which is here aluminium, you can, instead of typing the number here, you can type $1000 in this case, because we want to have 1 kilo, and it will automatically, if you press enter, it will automatically calculate the remaining balance for that element. So now if you click next, you're going to see the next window, which is the menu, and you see that when we loaded the example, all species that are necessary and solutions will be selected. So you have the gas, the solids, and the appropriate phases will already be selected for you. Here it will be already done, but if you want to do it from scratch, you can click right and select P for precipitation target and leave this temperature case blank here, so the program can calculate the liquidus temperature. The liquidus temperature is the temperature at which the first crystal starts to form in the liquid phase as you're cooling down. And this is important because we don't want any solid to be forming in the liquid while we are treating it. So here we can see the precipitation target is 646 degrees, and therefore we will set our temperature higher of about 100 degrees to ensure everything is liquid when we're performing when we're inserting chemicals, for instance. What we can see here in the window is that we have your scrap, you have your temperature, you have the composition of the liquid, and we also have the primary phase that is going to precipitate. And here you can see it's the FCC, which is not formed yet, but has an activity of 1. So it's going to be the first phase that precipitates. And you can see here the composition of the phase. It is really rich in aluminium. So now we're interested in the phase assemblage of the scrap. So what are the phases present in the solid state? So in order to find out that, what you're going to do is that you're going to write 300 degrees C in this window right here. And of course, the scrap that we're having exists at 25 Celsius. So why are we choosing such a high temperature? It's because typically below these temperatures, the diffusivity is so low that the equilibrium that is predicted at 25 degrees will practically never be reached. So it is not realistic to consider this equilibrium. And thankfully, there's a way to circumvent that, though. So as I said, we're going to choose this temperature, 300 C, and we're going to calculate the equilibrium at this temperature. So when we do that, we can see that all the phases that are in equilibrium. So we see the intermetallics D2H, which is a prototype, AC1, the aluminum manganese silicon intermetallics, and of course the primary phase that is FCC. Okay, so now what you want to do when you have all your phases and equilibrium at 300 C is that you want to save those streams so you can reuse them for further calculations. So in order to do that, you can go to Stream File, Save Solution, and select the phases that are here in equilibrium so you can save them. And then all you have to do is to repeat this process for all the phases that are present here. So now, of course, those streams, we want to have the properties at their property at 25 degrees Celsius because this is the temperature that we're using, that we're melting the scrap from. So here you can see when you load the stream, the properties here are at 300 degrees Celsius. So if you select initial condition, you see that when you calculate the enthalpy of melting, that it is not that it will not calculate the accurate energy requirement. So what we have to do is to take all our streams and cool them down at 25. So you have to load all the streams one by one. And then when you click next, you're going to select only the phase, that you're trying to cool down in order to conserve it. And you're going to select 25 degrees Celsius. And then you have to repeat the same process for all phases, saving all the streams, but at 25 degrees Celsius this time. So now we're going to move on to the second simulation, which is the furnace heat balance. So now you can open equi-ubc heatbalance.dat. So here, when you load the example, you're going to see all your phases that are imported at 25 degrees Celsius. And here you can select, you have to select initial conditions if we want to calculate the delta H of heating, so the enthalpy of heating from 25 degrees Celsius to 750. So if you click on next, you're going to be able to enter 750 in the temperature box and hit calculation. So now after calculation, you can see the result here. So if you scroll down, you're going to see that the delta H is given here in joules, and this translates to 1.17 megajoules per kilogram of scrap. So now you may ask yourself, why did we go through all the trouble to create streams and phases and save them? And is there any difference if we just consider the element that are present at the beginning? So the question really is, what is the effect of the phase assemblage on the heat balance? If we chosen the equilibrium of 25 degrees Celsius, will it change that much the heat balance calculations? So if we consider the equilibrium at 25 C, this is the energetic requirement that you will get. So you see that there's a small difference, which is about 20 kilojoules per kilogram. And I made a quick calculation on the, you can see here you underestimate the energy requirement. And if you make a calculation, you see that the amount, that the cost that you underestimated per ton of scrap is 1.7 Canadian dollars. And you can get this information using the heating efficiency of a reverberatory furnace in the worst case scenario, the energy density of coal, and its price. So now let's move on to the third example, which is the EQUI-UBC chlorination 1.dat. So this is going to be about melting the scrap and injecting chlorine gas in the furnace in order to refine the metal. So now when you load the example, we have all our streams at 25 that we had earlier, and we add chlorine with a parameter alpha that we're going to sweep from 0 to 5 moles. Here you can see that even though we're working in gram units, that you can introduce moles of Cl2, which is more convenient if you want to visualize the stoichiometry, for instance. So here you click next, you have all your phases selected, gas and the solids. The temperature is 750 Celsius like earlier. And the result here that we plotted from the simulation, from all the simulations at different amount of moles ejected. So you see here we did a parametric sweep from 0 to 5. And what you can see on the left is the percentage of alloying elements, so the composition of the liquid metal. You see that magnesium here is effectively removed from the scrap, and there is a little less than 0.5 moles of chlorine injected in order to fit the specification for the AA3104 alloy. As for the other alloying elements, you can see that their concentration increased very slightly with the number of chlorine, with the quantity of chlorine injected. And this is due to the fact that we are losing aluminum in the liquid. And the reason for that is that, as you can see from the graph, is when you don't have magnesium anymore in your scrap, your chlorine that you inject is going to want to oxidize something else. And the second most easily recycled alloy element here is aluminium. So as soon as there's no magnesium left, aluminium is going to be oxidized to aluminum chloride, which goes into the gas phase. And this is not a good thing because this is a substance that you want to avoid forming, not only because you're decreasing your yield in aluminium, but also because it is detrimental to the environment. You can see here, so this is only to show that this is magnesium chloride that is formed, that it stops forming as soon as there is no magnesium left. So the conclusion here we need to draw is that we need to control the flow of chlorine in order to avoid the aluminum chloride formation in the gas phase. So next is simulation, is using a salt flux. So the salt flux that we chose here is potassium chloride, sodium chloride, and aluminum chloride. So here we can see we're going to just add the salt flux to the scrap that is molten at 750. So now you can open the EQUI-UBC fluxin.dat. What you see here is all your phases that are present at 25, so like last time. And instead we have the flux salt that is present in the proportion that are taken from literature. So typically 45% of potassium chloride, 45% of sodium chloride, and 10% of aluminum chloride. So here again, we're going to enter the parameter alpha, which was going to be swept from 0 to 5 moles through steps of 0.1 mole. Here again, all the faces that are selected, then you can hit calculation. So now we have the same type of graph that are plotted. Here we can see the liquid composition, so the concentration in weight percent of alloying element. So now we see that the aluminum decreases with the amount of flux that is added, but the other alloying elements stay at the same level as we add the magnesium chloride. And the reason for that is that the amount of aluminium in the liquid is actually increasing as we add more molten salt. And the reason for that is that we're going to, of course, not all the magnesium is consumed here, but the more flux, the more molten flux salt that we have, we're going to produce more magnesium chloride, and we can here fit the specification for the A31 alloy. So what we can see is that there's an exchange of magnesium and aluminium between the flux and the molten salt. So now we can make a quick comparison between simulation 3 and 4. You can see that refining with the chlorine actually causes the loss of aluminium to the gas phase, while the refining with the molten salt flux causes, for the same amount at least, the aluminium content to increase in the metal due to the exchange between magnesium and aluminium in the scrap. You can see here in both cases that magnesium chloride is formed as a result of the reaction. So now finally, last simulation, we're going to just assess the effect of air on the aluminium molten metal, and just as a quick indication of why we can't bubble oxygen in the melt like we do for steel. So we can open aqueous UBC scrap with air. And here again, we're going to use the, we have all our scrap, and we introduce a variable amount of air, composed of course, oxygen and nitrogen. So here again, we can hit calculation, and we'll see the effect of increasing amount of air introduced in the furnace. So we see that quickly we lose aluminium from the liquid phase to the formation of aluminium nitride, which is in the form of wurtzit, and the spinel phase, which is magnesium aluminium oxide. So here we can see that dross is formed. This corresponds to dross formation. And this is why we need to work with a flux to protect the molten metal from air that is entering the furnace. This is not taking into account the effect of the presence of combustion gases, while that would be something interesting to assess. So to conclude, today we have used PackSage for 3 things. First is to determine the operating temperature and the energy requirement for the furnace using simulations number 1 and number 2. With simulations number 3 and number 4, we found the reactant consumption and the products that are formed for 2 classical demagging processes. And finally, we assessed the effect of air entering the furnace on the molten metal through simulation 5.